this video is a continuation of Chapter 8. We're going to continue on with an introduction to hypothesis testing. By the end of this video, you should understand the difference between a one-tailed test and a two-tailed test. Continue to understand the logic of hypothesis testing. Be able to state hypotheses, locate critical regions, but now for a one-tailed hypothesis test, and conduct a one-tailed z-test and make a decision. So again, we're transitioning here from the two-tailed test to the one-tailed test. So, what type of hypothesis test do you think we've been talking about thus far? Up here, have we been talking about two-tailed or one-tailed? You're still not sure. Let's go ahead and look here. Remember, this is our normal distribution, and here we have one tail, and we have a second tail. So that's a two-tailed test, and it's non-directional. When we stated our hypotheses, we didn't say which direction from the mean we expected the treatment to change things. We just said that our treatment was going to cause the mean to be, of the new population, to be different from the original population mean. So what we want to talk about now is a one-tailed test, and it is directional. So we're going to be saying that there's a specific direction of the treatment effect can be predicted, that we expect the treatment effect to increase or decrease scores. So the researcher specifies either an increase or a decrease as a consequence of the treatment. So again, we're talking about that sample mean, and so we're going to predict that either that sample mean is going to increase or decrease. So looking here, here's our sample mean, and here's this tail that we're predicting. So if we're predicting the tail on the right-hand side of the diagram, these are bigger numbers, right? So here would be a prediction of an increase. If later on you might see some examples where we're talking about the tail down here, that would be where we'd be looking for a decrease. I want to talk about that alpha level. And if we think about, we're going to stick with a 0.05 for now. Later on you might see some examples with a 1% alpha level. But let's think about this. We have our distribution, we have our mean here, and we have our critical z. Well, the idea is that all of this area under here, that's going to constitute that 5% now. We aren't splitting it into two. So, if we look over here, and we look at our table, we need to find that 0.5. And so the value we're looking at is going to be, we're going to go down here. So these are roughly about the same distance from that number 0.05 that we're looking for. So we're going to take the one that includes a smaller probability versus a higher probability. And so we're going to know that this 1.65 corresponds to a 0.05 alpha level for a one-tailed test. So the critical z, when your alpha is 0.05, your critical z is 1.65. This is just showing you here on that diagram again. Here we have our mean, and we have, for our z-score, 1.65 corresponds to the alpha of 0.05 for a directional one-tailed test. So now we're going to go through an example. So it's the same example that we did before in the teacher-led two-tailed hypothesis test, but now we're going to do it for one-tailed. Please go ahead and follow along with me. The calculations will be the same, but our decision could be different. So now we need to state the hypothesis. And if you remember, for a one-tailed test, it's directional. And so if you look here, this is the direction that we're predicting it's going, and here's our mean. So we're saying that the treatment is going to increase the sample mean or cause it to be greater than the sample mean. And I like to start with the alternative hypothesis and then go back and fill in that null hypothesis. So here, instead of using a doesn't equal sign, we say that the alternative hypothesis, or H sub 1, that the mean for training, the group that has undergone training, will be greater than that population mean. To state it into words, the training will increase the friendliness scores. So then what do we need to think about? All our null hypothesis. So if this is our alternative hypothesis, our null hypothesis is going to be everything else. So our null hypothesis, or H sub O, says that the mean of the group that underwent training is equal to or less than 30. So that our our group that underwent training, they're going to have a mean that's equal to 30 or less than 30. So now we need to set the criterion, and we already talked about this a little bit, so I'm just going to quickly remind you that we set the alpha at 0.05, and we looked at that unit normal table and found that that corresponded to a z-score of 1.65. So here's our critical boundary formed by our critical z-score, and this is our critical region. And so if our sample mean falls in this critical region, we reject the null hypothesis. So here I've highlighted some important information, and we're going to calculate the z-score. So remember, our z equals the mean minus, our sample mean minus the population mean over standard error of the mean. So if we plug those numbers into there, we have the mean on friendliness is measured by, we have our sample mean here is 40 minus our population mean, which is 30. Oops. And remember, our standard error is the same as our standard deviation because we have an n of 1. So if you don't remember, please go back and review the earlier videos that showed that. And that gave us a value of 2.5. So now we need to make a decision. So we have our calculated z is 2.5, and our critical z is 1.6. Remember, we got that from our alpha level. So now we need to decide if we're going to reject the null or fail to reject the null. So if we think about making a diagram here, and again, this is our mean, and here's our critical z of 1.65, where does this value fall? Is it here in this critical region, or is it in here? So in order for it to be in the critical region, it has to be greater than 1.65, and 2.5 is greater than 1.65, meaning that it's going to fall out here in this critical region somewhere, which means we reject the null. So as it would be written in the literature, the training program significantly increased friendliness scores, and then you'd write z equals the calculated z value with a p less than 0.05. Now, later on in the semester, I'm going to be giving you some SPSS data, and when you use SPSS, you're going to get a specific p-value that's associated with that data analysis, and you would actually report that specific p-value if you had that SPSS output. But for now, when we're talking about z-scores, again, you have z equals, and this is the calculated z-score with a p less than 0.05.